All right, welcome everyone. Today we have William who will tell us about Serre Spectral Sequence Part 2.
Yeah, welcome back everybody. It's good to see everyone here again. So the purpose of this talk is essentially, last talk I messed up an example. I didn't actually do anything incorrect. I just wasn't thinking properly. So I felt like really bad. I wanted to come back and redo the example so everyone can see how it actually works, because it's a really cute example. And I also wanted to do the show-off example again, the pi4 of S3, just because this is, the first step towards Serre's big calculation of all of these homotopy groups of spheres. This is kind of the steps that got him towards his Fields medal. But I couldn't just talk about that. It would be like 20 minutes or something. So we're going to move on to some, like I said, in the abstract, a bit of a more intermediate topics. The first thing is that there's some interesting exact sequences that are derived from the Serre spectral sequence. Well, the Serre exact sequence is kind of the big shining one. It's really simple to extract. And what that says, essentially, is if you have your fibration FEB, right? So if you start studying homotopy theory, the first thing you learn about a fibration is that it has a long exact sequence of homotopy groups. It's really trivial to just work out this long exact sequence. But for something like homology or cohomology, you don't have a long exact sequence, and that's why you need to introduce the spectral sequence. But it turns out that, based on the connectivity of F and B, so if the first non-zero homotopy group for F happens around degree n, first non-zero homotopy for B happens around degree m, then the sequence that you want actually does exist, and it is exact in a range up to about n plus m. So we'll see specifically what the numbers are because it just falls out of the Serre spectral sequence. It's really nice. The other one, the Gysin sequence, it's a lot easier to derive this by other means, but it's nice to see inside of the Serre spectral sequence is kind of it's just a demonstration of how much information the spectral sequence is providing to you. There's a lot of very detailed information that's contained in it that you can, after studying it for a long time, you just start extracting things about different vibrations. A bit more advanced at the end, and this is time dependent, this is something called transgression. So a lot of the times you try to do the spectral sequence, work it through like a Sudoku puzzle or whatever. But there will be some differentials where you'll have maybe you have a differential coming into something and a differential coming out. And all you manage to figure out is something like this one's non-zero if and only if this one is. And you can't really manage to narrow down the specific information that you want. Transgression is something that can help you to really pin down, well, at least it's a source of helping you to pin down what differentials are doing by exploiting something called cohomology operations. And so we'll see the cohomology operations are a little hard to calculate, but way back in the 40s and 50s, Steenrod developed this theory of Steenrod squares, the Steenrod algebra of cohomology operations. There's one cohomology, there's one Steenrod algebra for every prime p, and he worked out the Steenrod squares for mod 2 in the mid to late 40s. So this was before Serre spectral sequence. And then after the spectral sequence came out, all of this stuff was happening concurrently. You can't say that one was the influence for the other. Cohomology operations and the Serre spectral sequence calculations kind of fed into each other as this positive feedback loop. And so as an example of transgression, we're going to look at this space, KZ3. I have to draw that a little. Did the brackets wrong there. So this was the Eilenberg-Mac Lane space for Z in degree 3, meaning, again, remember, this means that there's one non-trivial homotopy group for this space, and it's Z, and it's in degree 3. And so we're going to, sorry? Yep. Write bigger? Okay, I will try to write bigger. This is just the intro, so hopefully it's not super crucial. Okay, this is the plan. Great. So first, let's recall what was happening last time. For a sufficiently nice fibration, like say E and B are both CW complexes, and B is path connected, and the homotopy, the fundamental group of B, acts trivially on the cohomology of the fiber, then we have something nice called the Serre spectral sequence. And the E2 page is given by cohomological information in terms of our base and fiber. So it's actually, you take the cohomology of the fiber as the coefficients in the cohomology of the base space. And so your degrees P and Q match up like that. And this converges towards the cohomology of the total space. Well, recall like convergence meant something really subtle. It meant that like there is a filtration on the base space that gives you a filtration on the total space, which gives you a filtration for the cohomology of E, which is the thing that you're trying to compute at the end of the day. And the E infinity page, so as we go through the spectral sequence, taking kernel modulo image to get to the successive pages, when we reach the limiting term, what this is calculating for us are the filtration quotients of the object that we're actually trying to calculate. And here I didn't remember what the filtration parameters were or whether it's plus or minus, so I just wrote or something, right? So the important thing to remember is that you get some filtration quotient as your E infinity term. And so as you walk up the anti-diagonal like this, so say like here's degree n, you want to compute the degree n cohomology of E, you have all of the PQ that add up to n. I should write bigger. All of the P plus Q that add up to n, and you're reading off the filtration quotients for the cohomology of E on the E infinity page. So in principle, you still have to sort of start at the bottom one. So the smallest filtration is actually the zero group. So the smallest filtration quotient is actually a sub-algebra or a subgroup of En. And then you have the next filtration quotient. Now you have to solve an extension problem. You have to say, okay, well, there's an extension of something by something. The actual filtration is like an extension of these two groups. You have to extend all the way up to the top to actually answer the question. But in all of our cases, we don't end up having to do that because we chose them so that they wouldn't be hard. Okay, next, we were able to think about the ring homomorphisms or graded group homomorphisms coming from the usual maps in our fibration, the projection map and the inclusion of a fiber. They're induced maps. We can find them inside of the spectral sequence. And we found was, right, on the E2 page, since you have the cohomology of B sitting on the bottom row, and you have the cohomology of F sitting in the first column, right? So the only differentials coming out of the bottom row are 0. And so the only way to change entries on the bottom row as you go to the next page is if they're in the image of the incoming differential. And so to get from the E2 page, or the cohomology of B, as the bottom row of the E2 page, to get to the E infinity page, you're just taking successive quotients by the D3 quotient by D4 quotient by D5. So there's a surjective map from in degree n, say, from the cohomology of B all the way down to the E infinity page at this square. But this square is like the lowest filtration of the cohomology of E. So when you project all the way down to the E infinity page, you're actually just a subgroup of the cohomology of E. And so that's the way that this map works in terms of the spectral sequence. And this other map is a little different, but essentially dual. So suppose you have like in degree Q up here. I'll be consistent with that and write a degree P there. If you have a degree Q up here, all the incoming differentials are 0. So none of these have any effect. The only way that you can affect this group at all is by having an outgoing differential with elements that aren't in the kernel of that. And so when you have an element that's not in the kernel of the outgoing differential, it evaporates. The only thing that survives are the elements that are sent to 0. So starting from the, which way do we want to go here? So starting from the cohomology of F as this first column, the E infinity page is just a subset versus the cohomology of B where the E infinity page was a quotient. So it's kind of upside down. So if you started at the cohomology of the total space, you end up in this square by taking like the largest filtration, which is the cohomology itself, and then quotienting out by the second largest filtration. So here I've written indices 0 or 1 because I don't remember what I did last time, so whatever. Let's say F0 is the biggest thing, F1 is the second biggest thing, and so this is like the last filtration quotient. So starting from the from the cohomology of E, you just quotient down to this, and this is a subspace of F, or a subgroup of F. So that's the way these two maps manifest in the Serre spectral sequence. And you can see in particular, well, I guess it's obvious that if you compose them, going from B to E to F, you should get 0 because the composition of pi and I is already 0. So by functoriality, you're going to get the 0 morphism. But you can also see that in the spectral sequence, because when you come in with something in B, right, you're in the bottom row, but then to get to F from E, you quotient out by like everything that's not in that last column. So you can see like how the composition gives you the 0 morphism in the spectral sequence as more than just a formal thing. Okay, that was just to like remember what we did last time. Does anyone have any questions that they had from last time or that they want like clarified? Okay, so let's jump into this example that I kind of messed up last time. So we'll see what I did wrong, and then we'll do it right. Like I said, I didn't actually do anything wrong. I just wasn't thinking clearly. Okay, so this is what we're starting with. We want to compute the cohomology of this space. And well, we know the cohomology of this space, and we know the cohomology of this space. So the Serre spectral sequence, let's just write it out, because this is the easiest way to make a mistake, because if you don't even think about what are the terms in your spectral sequence. So this is our E2 page, and we have it going towards the cohomology of a point. So we know that everything except for the thing in degree 0, 0 is going to, you have to get cleared out by the time we get to the end of the sequence. Okay, so our base space is the 3-sphere. So I've drawn this a little bit exaggeratedly. So we only have cohomology going up to degree 3. It's a Z there. And then we have, like I called last time, we have this terminator line, where everything to the right of this is 0. Yeah? And now we want to start to fill in the column. Our goal is to compute the column of the E2 page, knowing that the E infinity page is 0. Okay, so what do we know about loops of S3? So since S3, the first 2 homotopy groups are 0, long exact sequence of the fibration for the homotopy groups is going to tell us that loops of S3 is simply connected. So we can put a 0 here by simple connectivity. So we have an entire line here at 0, line here 0, this whole bottom row at degree 1 is 0. So we know we have to get rid of this, and let's name this generator something. I'm going to name it mu, because that's how I always name my generators for the spheres. We know that this has to vanish at some point. The only possibility of getting rid of it is on the D3 differential, which means that this generates a copy of Z. This D3 has to be an isomorphism here. Okay? Now we can actually fill in all of the groups inductively. So since this is Z and this is Z, this guy here, because everything's sufficiently spaced out, universal coefficient theorems are going to tell us that this is actually just a tensor product. Since everything's spaced out and everything is just Z, we're actually going to get this. So if we take a copy of Z here, a copy of Z here, if we choose a generator of this and a generator of this, a generator of the tensor product is going to be the tensor product of the generators. So if we say here, let's call this iota. Sorry, I called it kappa. Kappa 1. Then a generator for this group is going to be the product of these two things. So it's going to be mu with coefficient kappa 1. Okay, so this was the start. This is all completely correct. Now let's figure out, okay, so a similar game reveals that this has to be 0 because there's nothing here that's going to get rid of it. And then this has to have something to get rid of this class. Okay, but what is this something? So we know that D3, so we know that there's a kappa 1 squared there, potentially. D3 of kappa 1 squared is equal to, if we apply our Leibniz rule, we're going to get 2 times kappa 1 d kappa 1. And this was 2 kappa mu. Kappa 1 mu. So, or in other words, 2 times generator. This was completely correct. This is what I did last time. So this is telling us, right, since this has to be an isomorphism, because this is the only opportunity we have to clear out this group and this group. Since this is a generator, and kappa 1 squares to 2 times, or rather it squares to something that goes to 2 times a generator, that means kappa 1 itself has to be 2 times a generator. And I'll call that generator kappa 2. So there's a generator, kappa 2, in H4 loops S3, so that kappa 1 squared is equal to kappa 2. Okay? So this goes and hits this generator. Then, like inductively, we find a generator for this group is described as kappa 2. Yep. Okay. Now we run into the place where I got confused last time. And I consider kappa 1 cubed up here in degree 6. I'll extend this up by 1. This is going to be 0 as well. Kappa 1 cubed up in degree 6, if you apply the Leibniz rule, you get 2 kappa 1 squared d kappa 1, which is mu. So I thought, the answer should be, 3, because it's supposed to be n factorial, but I'm getting this 2 instead. So I was looking at my notes, I was looking at the board, I couldn't reconcile these two calculations. Can you see what to do next?
Is kappa 1 squared 3 kappa 1?
Kappa 1 squared. Oop, I did this wrong. Now I made a mistake. See, this is how you can find the mistake, is you check my calculation first.
Kappa 1 squared is 2 kappa 1.
Yeah, we just did that. We just showed that kappa 1 squared is 2 times kappa 1.
That's where you get the factorial.
Yeah, so the point that I was confusing myself about was I was saying, oh, well, this must be a generator, so we must be, having a contradiction. But this isn't the generator. Kappa 2 mu is the generator. So this is 3 times 2, kappa 2 mu, right? Or 3 factorial times kappa mu. So therefore, there must exist a kappa 3. So that kappa 1 cubed is 3 factorial kappa 3. And now that's the new generator. So you can see how the inductive argument would work if I would actually set it up properly, right? You take your kappa 1 n plus 1, you'd apply your Leibniz rule and get n plus 1, kappa 1 to the n, d kappa 1, which is, by the base case, mu, and then you apply the inductive hypothesis, right? This should be n factorial kappa n, mu. So that's where you get your factorial from. This should be an n. My ones look too much like n's. Okay. n1. Sure. Okay, kappa n mu, where this is a generator. And so then you know that there exists a class kappa n plus 1, ... Okay? So so the result of the calculation is you can take your kappa 1, take some huge power of it, and apply the differential to it. So if you know that all of those powers of kappa 1 are already non-zero, then the image of that differential, by computing it using the Leibniz rule, is also going to be non-zero. And you have to iteratively figure out, the powers of kappa 1 overshoot a generator. Exactly how much do they overshoot? And you can inductively find out it's by n factorial. Okay, so the answer that you get then, so it looks like you have a polynomial ring. Well, you have a bunch of different generators for this polynomial ring, and you found one set of relations between them. And you have to ask, okay, well, have we actually solved the problem? And the answer is yes. But you still have to check. You still have to check to see that you actually have enough relations. So I'll leave that as an exercise, but just write up what is the answer. So the result, so the integer cohomology of loops of S3, you can write it as a polynomial ring in countably many classes where kappa n is in degree 2n, modulo the relations given by kappa 1 to the n is equivalent to kappa n times n factorial. So it's this weird sort of factorial algebra. And like I think I wrote down last time, you can express this in a different way. You can take all of the same generators, but instead of putting all of the emphasis on kappa 1 as somehow the most important thing, you can actually just express this in terms of taking the product of any two generators, and you're going to get n plus m, choose n, or equivalently choose m, of the one in the appropriate degree. Yeah. So that's a good one. Right, so how would you actually like check and verify that this is the right ring? Okay, well, like this is the same game that you would always play. You have some ring that exists, and you're trying to figure out this ring. And you have a bunch of elements in this ring that you know span the ring. Then if you just take the polynomial ring in those elements, you get a free map to your ring by just sending everything to itself, essentially. And since it's this is a spanning set, this is a surjective map, and you say, okay, well, then the ring we're trying to figure out is really this polynomial ring modulo the modulo the kernel of whatever this map is. That's just the first isomorphism theorem. So then you think about, okay, look at all of the relations that we already have. All of these relations of the form kappa 1 to the n is n factorial kappa. So we know that that's contained in the kernel, so that this quotient ring gets a map to the ring that we're trying to figure out, this ring. Right, so you can easily write down a map going this way, given that these are the generators and these are relations that we know are satisfied. And then the question that you have to show is that this is an injective function. So it's already surjective, you just have to show it's injective, meaning that if you have anything else in the kernel, you just have to show that that's an element of the ideal, generated by these relations. So that's not really like a profound thing. This is just how you would go and check this is how you normally check that a ring is isomorphic to some presentation in terms of generators and relations. And I'll leave that as an exercise to go do that. Okay, so that was fun. Any other mistakes that I made? Does anyone see a problem? Yeah. So my mistake last time wasn't really an error. I just forgot at the time that those weren't really generators. And I just got really confused, and I couldn't reconcile what was on the board with what was in my hand, even though they were saying the same thing.
You write kappa 1 squared equals kappa 2.
Oh, that's not right.
Yeah.
Yeah, so that's like obviously wrong.
Okay.
Yes. The whole point was that it's 2 times kappa 2. Because then we use that inductively right
Yeah,
there.
we said it verbally, but
Yeah, we said it verbally. Yeah.
but on the board is.
Oh, good point. Yes. Your job as the audience is to make sure that I don't make like glaringly obvious errors like that. Thank you. Yeah.
I'm sure if there are mistakes that comment, people comment will for that.
The YouTube comment section. Yeah, definitely. Yeah, leave your likes and replies in chat. And subscribe. Okay, example 4. The calculation for this one, once you actually have it set up as a spectral sequence, is a lot easier than the last one we just did. The hard part is to set it up correctly. Okay, so how are you going to compute pi4 of S3 using a spectral sequence? So the idea that I briefly mentioned last time is you can start with your S3, and you want to kind of do this destructive process where you peel off the bottom-most homotopy group to make a new space that has all of the same higher homotopy groups as S3 and has a map to S3 that you can at least turn into a fibration whose homotopy fiber is manageable, something that we already understand, or at least something we can compute. So here's how it works in practice. We know that pi3 of S3 is Z. So you can construct fairly easily a map from S3 to KZ3, mainly because you can construct a copy of KZ3 by starting with the 3-sphere and then adding on spheres of dimension 5 and higher. So this is almost an inclusion map of S3 into KZ3, which is an isomorphism on pi 3. Okay? Just because like this is the 3 skeleton of this, and you only ever add things in dimension 5 and higher. Okay, and so what we do is we take the homotopy fiber of that. What do I want to call this map? C. Yeah, let's call it F. So if we take the homotopy fiber of that and then just look at the long exact sequence in homotopy groups, what we're going to get is that pi k of hofib, well, I have a name for it, it's called F. Pi k f to pi k s3 is an isomorphism when k is at least 4, and pi k of f is 0 for k less than 4. So all we've done is we've just peeled off the bottom homotopy group of S3, and we even have a map between them that induces isomorphisms on all of the higher ones. Okay. Pi 3, yeah, k less than 4. Yeah, pi 3 of S is 0. This was the whole point of doing this, was to take off the bottom pi 3. Yeah. Okay, so by construction, this is a fibration. The thing that's not great about this is that KZ3 is something that we haven't even tried to understand yet. So what we can do is we can apply something called the Pupa sequence to push this fibration kind of to the left by taking a loop. Pupa sequence. So this is something that you would see in like your first kind of serious attack on homotopy theory. So if FEB is a fibration, I'm going to call it a fibration sequence. So by fibration sequence, I mean that there's a pair, that there's another triple of spaces, F prime, E prime, B prime, and homotopy equivalences between them, making the diagrams commute, such that this bottom row actually is a fibration. So this is a very, like a generalization of a fibration in that it has all of the same homotopy group stuff. Like there's a long exact sequence for a fibration sequence. You just have to turn it into like, realize it as a fibration first. This isn't really the same as fibrant replacement. It's not the same thing. So if you start with a fibration sequence, then you can extend it to the left with loops. So you can go B, E, F, loops B, loops E, loops F, loop squared B, dot, 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 is also a fibration sequence. Meaning that like you can take any 3 successive spaces, for example, and say, okay, we can actually represent this composition of maps as a genuine fibration. And so a consequence of this, you can go read this in a book. It's really good stuff. I don't have time to really prove it for you. A consequence of this, of course, is if we take this fibration, push it one to the left with loops of KZ3, remember that loops of KGN, if you go and look at the long exact sequence of homotopy groups, what this does is it pushes the N1 down, KGN minus 1. So we actually get a fibration from KZ2 to our homotopy fiber to S3, where KZ2, I've mentioned a few times already, that's a CP infinity. So we've done that one. We've done that one, and so now we can use that calculation that we did to figure out the homology groups of F. And since F is 3 connected, we'll be able to use the Hurewicz theorem to say, aha, the 4th homology group is the same as the 4th homotopy group. So I'm going to point that out here. I should have pointed that out earlier. Because of this properties, H4F is the same as H4 pi 4F. And so if we use a Serre spectral sequence to compute H4F, then we will get pi 4F by all of the machinery that has been set up by all of these very good people. So nuts, in other words, let's do the Serre spectral sequence for this fibration. Okay. I don't think I forgot to set anything up. All right, so the first step in any Serre spectral sequence is to write it down. It can really help you psychologically just to have this piece of text in front of your face. The fibers are CP infinity. And this is converging to, this is one of the examples, we haven't done a lot of examples so far actually, where we're actually computing the cohomology of the total space. All of the time we've known like the fiber or the base space, and the total space is contractible, and so you have to sort of figure out one from the other. This is like, okay, we know everything about this, and we're just trying to turn the crank and figure out the E infinity page so that we can say, well, what is this? All right, so this is easy. We have another one of these where the base space is S3. We like those ones. Towers of zeros. Here's our Q. And we know everything about this ring. We already computed this last time, right? So it's generated by something I'll call iota, even though it kind of collides with the last talk. That's okay. I always use iota here, iota squared, iota cubed. Okay? Okay. What do we know? Okay, we can also figure out what is this stack up here. Yeah, we haven't filled everything in yet, so we still have things. Okay, so if we take our usual orientation mu, and then this stack living above mu has these generators. Dot, 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 okay? And as we recall, I'll use color because Daniel likes when I use color. We had a terminal line here, the terminator. And we have differentials D3. So because of the way that this spectral sequence is spaced out, D3 is the only differential that has any hope of doing anything. And unlike earlier ones, we don't have to clear everything out. We don't know what the end result is yet, so we can just figure out what these D3s are. Okay, so the first step, there's one piece of information that we haven't used yet explicitly in trying to set up the spectral sequence. So remember way over here, I made a big deal about the fact that the pi 1, 2, 3 for f all vanish. So that means that the cohomology in degrees 1, 2, 3 for f also vanish. But we're working our way towards this cohomology group. So the first non-zero cohomology group of f happens in the 4 line, okay? So if you take your degree 4, and down here, we have our degree 4 out in the terminator zone, right? And we collect those together, right? This is the first non-trivial cohomology group of f, is that line. So that means that everything below that line has to get cleared out. Do you see that? Does that make sense? You look very confused. Yeah, so because like, yeah, maybe I draw it in like bigger squares so that we can see more clearly. So these squares that I'm drawing here, those are going to be the filtration quotients for our H4. But H3 is 0, H2 is 0, H1 is 0. Oh, sorry, I did something really weird. How did I not count? No, I can count, don't worry. Don't worry. I know how numbers work. Okay, so there's 5 there. Yeah. So these are the first non-zero things on the E infinity page. Everything else on the E infinity page other than that Z has to be zeros. This means that this D3 has to be an isomorphism to take those out and to make F actually 3 connected. So the first thing we say is that F3 connected, meaning the first 3 homotopy groups vanish, imply that D3 of our generator iota is also a generator mu. So that's the first, that's kind of like the key that makes the entire computation run. So this is a whole sub-ring. This is the domain of every potentially non-zero differential. We know what the differential is on the generator. Now we can just compute it for every single value in that ring that makes up our column. So, right, we apply our Leibniz rule. And we get, okay, this time though, last time there was the confusion with generators, this time this expression actually is a generator. So our D3 going from H to N or rather I'll just write it like a spectral sequence, H2 in degree 0, comma 2n. This maps to, sorry, this should be 3. This maps down to the third column, so this is 3, comma 2n minus 2. This differential is multiplication by n, right? Takes a generator in this group and maps it to n times a generator in this group, where this is, I can write this more commonly as H2n Cp infinity, and this is H2n minus 2 Cp infinity with coefficients in H3 of S3, or since we've already like fixed a thing, this is really just, you can make this identification. Let's not. Yeah, let's just leave it like this. Okay. So it's multiplication by n, which means in particular all of these are injective. For all n, say. For every place that's non-zero that has a D3 coming out of it, that D3 is injective. So when you go to the E3-4 page, this entire column is now gone. So E4 of 0 to n, where now n has to be positive because we'll always have this one in the bottom corner. And for all time, because that was the last time a differential could have any effect, this is 0. There is no kernel coming out of that spot, and so you get a 0. On the other hand, all of these differentials definitely are 0. So on the E4 and hence E infinity page in this column, what you're going to get is Z modulo the image of D3. And so that's on one hand, and on the other hand, E for, how do I write this, 3, comma 2n minus 2, and this is, of course, the E infinity page as well, 3, comma 2n minus 2 is Z mod n. Okay, so that's done. We computed the E infinity page. So now we just have to wrap up and say, okay, well, what is the very poorly named F? What is its cohomology? And you'll notice, because of which groups actually ended up being 0 and which non-zero, you'll never find two non-zero groups in the same, right? This whole thing is 0, and these are like, yeah, why don't I draw the E infinity page? Yeah, duh. Okay. Let's actually look and see with our eyes. Okay, so this is the E infinity page. And I don't want to go all the way back for the red chalk, so you'll have to imagine that that's red. So we have Z, and then we have a bunch of zeros. These are also 0, 0. So right away you have no extension problem. That's a 0, that's a Z mod 2. This is a Z mod 3. This is a Z mod 4. So what are my degrees? I should make this more clear. 2, 3, 4, 5, 6, 7, 8. Am I doing this right? I think so. This is a Z mod 5. So on the E infinity page, you just have this tower of quotient groups. And so any anti-diagonal is going to hit them exactly once, and so there's no extension problems. Your cohomology of your total space, which I very kind of stupidly called F, is going to be 2n minus 1 of F is going to be isomorphic to Z mod NZ, because this is the place where, wait, what is, hold on, let me do math. 3 plus 2n minus 2 is 2n plus 1, right? So 3, 4, this is in degree 7, right? So H7 is Z mod 3, right? What is that? If I plug in a 3 here, yes, good, great. And what, H2NF is 0 if n is bigger than 0. So there's our answer. So we have the cohomology for our f. But like I said right here, we actually want to use the homology so that we can deduce by the Hurewicz theorem that H4 is Z mod 2. Because when you look at this, did I screw up my degrees somehow? No, I didn't, not yet. Okay. So like this is nowhere near degree 4, right? So 3 plus 2 is in degree 5. That can't possibly be right. And it isn't right because we've only computed the cohomology. So let's see how to compute the homology. And I'll do it right here. And hopefully you can remember the stuff that I'm just about erasing. Probably write it down in the same place.
Is this right underneath the You're saying H2n is 0. Where's the C mod 2 line up? What row is that?
So this is, yeah, I drew this really badly so they look like boxes, right? So this is 3. Wait, what am I? No, hold on, I'm being stupid. I had it. I just said what it was, right? So if this is in degree 3 plus this is 5. So this is in like degree 5. So 5, yeah. So here's 5, 0, 4, 1, yeah, 3, 2,
Oh, okay.
and then this, and then down off the bottom.
Okay,
Yeah.
I was thinking your n is p plus q. This is your degree.
Yeah. So this,
okay.
yeah. Yeah, this whole thing is my p plus q. The whole sum of those two. And so over there on that board, when I had E infinity and the bi degrees, I just added those together to extract this result. Yeah. Okay, so we want homology, which means we use the universal coefficient theorem. So I'll just write this in. So if we have some space x and we want the cohomology of x, this maps surjectively onto homomorphisms from the kth homology group of x to z. And the kernel is a strange x group from hk minus 1 of x to z. And so this kind of gives descriptions of your space. Notice that as homomorphisms to z, this is a torsion-free group. And if you go and look up tables about what Ext does when you try to compute it, so if this is a finitely generated abelian group, it's going to have a free part and it's going to have a torsion part. If you plug in Ext ZZ, so Z only has a trivial extension over itself, that's going to be vanishing. So what this is going to pick up is your torsion part of HK minus 1. So this is actually a torsion group. So this is actually the torsion of HK minus 1. And this is like the free part of HK. And so we know this, and we want to reverse engineer what HK is. And I think because I don't want to like slog people down too hard, you can work it out so that H2K, it turns out you just take these values and shift them down 1. That's the end outcome of analyzing this in this case. You just shift them down 1. So H2K of F is Z mod K. And now the odd homology groups vanish. So therefore, like we said by Hurewicz, because F, the first 3 homotopy groups vanish, turns out that pi 4 of F, Hurewicz map is an isomorphism to H4 of F, which is what you get when you plug in K equals 2. And like we said at the beginning, we constructed F specifically to have the property that pi 4 of F was isomorphic to pi 4 of S3. We even had a map that realizes it. So this is the, this is the computation. This is an interesting computation because it's not just a spectral sequence. It's also surrounded by a lot of really fundamental homotopy theory. So it can be instructive to people who even are like, if they're super familiar with spectral sequences already, and this is a really easy computation to do, you get to see some of the context that these calculations fall into and kind of expand it. Okay, so that was that one. Are there questions or mistakes that I made? There's probably some mistakes. Yeah, so just in terms of the broader relevance of this example, I should say something about stable homotopy of spheres and the Freudenthal suspension theorem. Just a really short statement so that you can see some of the big context. Okay, so suspension gives us a map. If we have pi k of some space x, what you can do is you can suspend x, you can suspend the domain of your maps from the k sphere to the k plus 1 sphere, and we get a map like this. From pi k of x to pi k plus 1 of the suspension of x. So Freudenthal, and this was, I made a point to look this up, this is 1937. So that's how classical this stuff is. Freudenthal says that sigma is an isomorphism. Specifically for, let's look at spheres. More generally, it holds if n is, more generally it holds if x is n minus 1 connected, but let's just state it for spheres. So this is an isomorphism if, what is the specific range on my page? N is bigger than k plus 1. And something that you don't often see written down, but I don't remember where I saw this. I'm sure it's true, but it's not on Wikipedia. It's a surjection in the case that n equals 4 is actually at the upper limit. So it's an isomorphism in all of these degrees, but in the degree 1 more, you still get a surjection. So in our case, if k is equal to 1, then 3 is bigger than k plus 1, which means that pi 4 of S3, this is already stable. And the map coming from pi 3 of S2 is surjective, and we know that this, from other stuff, from the Hopf fibration specifically, we know that this is Z, and it's actually generated by the Hopf map from S3 to S2. So this Z mod 2 is actually generated by the suspension of the Hopf map. So we actually have an explicit model for something that gives us something non-zero in this group. So that's neat. Okay. Oh, how long am I? That was a good time to ask for that.
50 minutes in, so
Almost an hour?
1 hour.
Wow, okay.
10 minutes left.
That's kind of, sort of how I thought it would go. Okay. Good. Yeah, my geometry teacher, Ty, Euclidean geometry, he always takes a break halfway through and he tells a really bad joke. I'm not that funny though. I don't have any bad jokes, I'm sorry. I'm not going to try to steal anyone else's shtick. Okay, so those were the examples, and that concludes last week's talk. I obviously planned too much stuff. Okay, so let's get on the road. And I'm going to start section 2 now about exact sequences, and I'm going to talk about specifically the Serre exact sequence. This is something that's definitely worth seeing. Okay, so suppose, here's the setup. F, E, B, the usual nice kind of fibration. And suppose that F is N connected and that B is M connected. So, like I mentioned verbally, this means that the first N homotopy groups are all 0. And this isn't like a strict thing. Like you still could have, right, N plus 1 connected implies N connected, right? This doesn't necessarily mean the next group is non-zero. It just means it could be non-zero. You know for sure that the first N are 0. Okay, So now let's consider the Serre spectral sequence for this fibration. I'll draw it really big, and I'm going to write it out because I keep saying that we should always do that. So if I didn't, it'd be a little bit cringe. All right, this is what's happening.
P plus Q, then Q looks like the same.
Yeah, it's losing stamina maybe. Okay, so let's put in these assumptions. Okay, so here's down in degree 0, z. If f is n connected, let's say here's n, that means that we have zeros all the way down like this. If b is m connected, here's m, then we have zeros all the way, oops, on this side, zeros all the way down like this. Okay, so what we can do is we can fill in our big, what do you call that? Epoxic zone? Something like that. So I'll color in red everything that we know to be 0. Right. Yeah, so the red zone is everything that we know is 0. And let's just give this group a name G and this one H. And then by the usual business, this is going to be a G mod 8, or a G tensor H in that spot. Okay. So let's think about what differentials can possibly happen. So if you have differentials connecting to this or this, right, there's a big wide band where like the first n or m pages are going to have like nothing going on. And in fact, we can get like a really specific estimate by just looking at the differentials coming into this one. So these are going to be our dRs for some range of r. So these are all going to be 0 until eventually you hit here. Okay, so what is this degree? This happens in a degree where m plus n, right? So this is by degree m plus n, and the right way to think about it is like this. The differential moves us over by m, and so it has to move us down by m minus 1. So this is in degree n plus m minus 1 is where this differential happens. And this is on the dm page. Okay? So the thing is, if you started anywhere below this, then you're going to get a differential that completely misses this block, and you're going to land all the way on the bottom after some time. This is an important phenomenon, is when you have something from the column that makes it all the way to the bottom. And this is going to be like our first little glimpse of this. So what am I saying here? So for q less than or equal to n plus m plus 1? Why do I have a plus 1? Have I done something stupid? Uh-oh. Hold on. No, I have. I've done a dumb. Yes. This is n. This is m. I made it I really spelled out what it means to be n connected, and then I did precisely the wrong thing. So this is an n plus 1, and this is an m plus 1. Which means that now, this is in degree n plus m plus 2. And so the differential is coming for an m plus 1. Yeah, so anything that's strictly less than that is going to be good. So for this, HQF, I'm not sure how I did this. Maybe we'll have to figure it out together. ZQ, and this is what we called the kernel of all dr for r less than or equal to q. So if we have that for anything there, then HQ, yeah, the differential coming out of length q. Yeah, but then for, I'm not sure what I was thinking when I wrote this. I'll just transcribe it, and then maybe somebody makes sense of it. think what I'm doing is I'm just, what was my bound on my R? My R can also be in this range. Okay, sure. So I think all I'm doing here is saying that as long as you live like here, and as long as you live like not too far out that way, you can faithfully identify these elements in the column with the groups of the fiber, and the elements in the row with the groups of the base space. As long as you don't get too far out where the differentials can make a difference. But as long as you're low enough down that the only differentials that can possibly do anything take you from the fiber to the base, then your fiber and your base have the cohomology that you actually want to think about. And so the Serre exact sequence, and I won't verify exactness, but you can see anyway where the morphisms come from, is you're going to start in degree 1 or 0. I figured out 1, I don't know. At this point, I'm just reading off my sheet. So the first differential, right, from h1 of f is now going to h2 of b. This is now d2. Right, so it's on one hand, it's interesting that the sequence is constructible using the Serre spectral sequence, but on the other hand, it's the fact that it's actually exact, which is not, I don't think it's totally trivial to prove. But the boundary maps are actually the differentials themselves. Right, so if you are in this degree here, n plus m, then the differential is going to take you all the way down to n plus m plus 1. And you're going to like just barely miss the corner of this big non-zero stuff. So this is the differential dn plus n plus 1. And so you're going to get your exact sequence up to this degree, and then you're not going to be able to go anymore. And you end up at the cohomology of f, and now you're stuck there. Because, done. Because by the time you get to the next differential, there's something in the middle which might have made it so that this group isn't f anymore, and that this group down there isn't the cohomology of b anymore. So then you might be able to find a very clever exact sequence of other stuff. But from just the connectivity, from the fact that we have this huge, huge dead zone, we can actually figure out that, oh, the thing that we want to be a long exact sequence actually does exist up to a range that depends on the connectivities. Okay. You're still doing, okay. Or, yeah, our camera guy's falling asleep. I'm trying not to blame myself, but he says he's tired. Yeah, so some immediate and simple corollaries of this. I wish I could use that last board because it's funny coming all the way over here. So example. So x, n connected, start with an n connected space. If you take its loop space now, this is by the long exact sequence of the fibration, n minus 1 connected for the long exact sequence in homotopy groups. Now that we have like a cohomology exact sequence, I guess I have to clarify. But I'm not sure if you would call this a long exact sequence because it doesn't continue indefinitely. It's just an exact sequence. Medium exact sequence. A moderate exact sequence. So if you take these two spaces, we know that they fit into a fibration, right? Loops point x. And so, yeah, what is our thing? Our n plus m plus 1 is now 2n. So we can plug this into our long exact sequence and figure out that hk minus 1 of loops x gets a map to hk of x, and it's an isomorphism as long as k is less than or equal to 2n. So in fact, loops, if we apply it directly to loops, we see that the loop space of x and the loop space and x itself, yeah, the loop space of x, its cohomology is kind of just shifted by 1 from the cohomology of x itself. And so if we have a very specific loop space, corollary, that's not how you spell it. What do you get? Loops of kgn, I've mentioned already. This is a kgn minus 1. So you get a really interesting, as long as G is abelian, sure. So for all k less than 2n, cohomology in degree k minus 1, kgn minus 1, is isomorphic to the cohomology of kgn, which is suggesting to us that there's actually like a stable value. There actually is a stable value, a stable range of elements in kgn. So you can take like limit of what? K goes to infinity of h n plus k, k, g, n plus k, something like that. That this has like is attained at some finite value. Yeah, so we have these stable homotopy groups of spheres. Because spheres in suspension don't play well with homotopy, you can't just say that you have an isomorphism all the time. Similarly, loops and homology don't play well with each other, but somehow we still have a stable value for these Eilenberg-Mac Lane spaces, which are sort of, in terms of homotopy theory, they're the atomic building blocks in the same way that spheres are the atomic building blocks for CW complexes in homology theory. So it's important that we actually have this, this limit, and if we have time for transgression, you'll see why that's important. Yeah, I'm not going to say anything yet.
1 hour left.
1 hour left. Okay. Okay, in that case, I'm going to say something brief about the Gysin sequence. And then I think we have time to say some things about transgression. Yeah, I'll keep that up. Okay, so you might remember when I was talking about characteristic classes, and Tom classes and Euler class, we had something that goes like this. So if, let's say let's say V to be is an oriented vector bundle, and SV, and I'll say pi bar is its projection map. The sphere bundle, yeah, let's suppose it has a metric, so we can just talk about sphere bundles. And let V0, let's just let this be the set of non-zero vectors of V. Which you can think about as just being V minus a zero section, right? Okay, so then we have a long exact sequence. Consider the long exact sequence in cohomology for the pair V0. So think about the entire total space of the vector space, and now consider the subspace of non-zero vectors. And now let's consider like a relative cohomology group of that. Okay, so long exact sequence of a pair is very basic and standard. I'll use actual numbers here. K, K, V, V, K plus 1. And then over here. Okay. So remember the snake lemma. If you have a short exact sequence of chain complexes, which you get from these three spaces, So, V0, V, and this pair give you a short exact sequence of co-chain complexes, and their long exact sequence coming from the snake lemma gives us this long exact sequence of the pair. Okay, so now we can start thinking about topologically what are these spaces. So V is a vector bundle. I'm going to leave myself some room here. V is a vector bundle, and so the projection map to B gives you an isomorphism. And in fact, inverse can be given by the 0 section for B. So we can just take this isomorphism pair between those two. Over here, the set of things that's non-zero, well, in a vector space, if you remove the origin, that deformation retracts onto the sphere, assuming that you have inner product in that fiber. So if you have a fiber bundle whose fibers are inner product spaces, like a vector space with a metric, then the deleted one, everything minus the 0 section, the metric lets you deformation retract that onto the sphere bundle. And so this thing is actually giving you cohomology of the sphere bundle, and let's name some maps. So SV includes into V0, and this includes into V. Let's call this I, let's call this J. And then we have B downstairs, and all of these projection maps obviously commute with each other. And there's a third one for V0 that I just won't write down. Okay, so the inclusion of SV into V0, that's a pullback map, J star, as well as like the normalization map that I just described with my hands. Let's call that eta star. Right, that's a homotopy equivalence pair, so that gives you a pair of inverse isomorphisms between these two groups. And if you fill in this map, right, according to this diagram, it says that if you fill in this map with pi bar star, then this little square commutes.
You said the metric allows you to deformation retract, but do you need to have a metric?
No, but, well, sort of. In order to say a sphere bundle, you pick out your sphere with your metric. That's one way to have a sphere bundle, anyway. More generally, you can construct a Gysin sequence for just an oriented bundle whose fibers are spheres. Oriented in the sense that, like, you've chosen an orientation for each of the fibers so that the fundamental group doesn't, like, swap those two in cohomology. Because you always have this, like, assumption that your fundamental group is acting trivially on the cohomology of the fiber. Otherwise, you have to introduce twisted coefficients. And that's like an entire other book. This is an introductory talk, so we're not going to get into twisted coefficients today. Yeah, but yeah. Question, I guess the question, unless someone didn't hear, was if you need a fiber to actually do all this. And I'm saying, I guess not really, but it's really convenient, so just do it.
Can you just do with the oriented fiber frame bundle?
Frame says orthonormal, so you have a fiber. That's what a frame is. It's an orthonormal basis. So you have a metric, not fiber. So you already have a metric. Just if you want to say the word frame, you have a metric already. Yeah. Thing about metrics on bundles, as long as your base space is paracompact, there is a choice of metric, and the space of choices is contractible. So it's like whether you want a metric or not, you've basically already chosen one, up to homotopy.
Up to homotopy is unique, yeah.
Yeah.
Right.
So like you shouldn't be too afraid of like choosing a metric. It's not that bad. Okay, so that accounts for these, right? The next one is this. So if you remember all of this discussion about Tom spaces, so I'll just describe this verbally. Okay, if you have a metric, then your Tom space is the disk bundle of that bundle modulo the sphere bundle. Okay, so consider this pair of the total space relative to everything that's not zero. You can take all the non-zero things and deform that continuously to all of the things with norm at least 1. So you take everything non-zero and you make yourself some breathing room by pushing it out to the boundary or to be like the complement of the unit disk bundle. And then when you take the quotient of the big thing by the smaller thing, that's the same quotient as just taking the disk bundle modulo the sphere bundle. So this cohomology group of pair is actually isomorphic to the cohomology of the Thom space of this bundle, which is the disk bundle modulo the sphere bundle. And then by the Thom isomorphism theorem, since we've assumed that this is an oriented bundle, Thom isomorphism says that our base space gets an isomorphism to this by cupping with the Thom class. Now I wish I'd given myself even more room, so I'm going to make space right that bigger. So by cupping with the Thom class, we get an isomorphism from the cohomology of the base space to the cohomology of the Thom space. And if you wanted to trace this whole thing around, cupping with the Thom class and then pulling back down by the zero section, well, by definition, the Euler class is the pull down of the Thom class. It's Z star of the Thom class. So this map actually is cupping with the Euler class of your bundle. Okay, and then we have a kind of mysterious boundary operator here. So here's again our Thom isomorphism, which is like cup by tau. And I'm going to call this one del bar. So del bar is really you do, which I'm going to say eta star and then delta, the usual coboundary operator, and then you cup with tau. Inverse, yeah. You do this, and then you do cup with tau inverse. And what I would say this is kind of like doing, what? Coboundary of thing, and then divide by the Thom class somehow. Somehow, morally speaking, this is doing a coboundary map, and then cup dividing by the Thom class. So someone should have yelled already. So the Thom isomorphism reduces the dimension of rank n. So cupping with the Thom class is going to increase the dimension by n. It's the isomorphism. And so, yeah, the Euler class also lives in degree n, so this makes sense with these. Now this is minus n plus 1 with b. Okay, here it is. So a little mistakey, but not too bad. So this sequence here that we just derived from the long exact sequence of the pair, this is the Gysin sequence. Okay. So this is what you can use to compute all kinds of classifying spaces cohomology. So use this to inductively compute H star of, say, BUN in terms of Chern classes, H star of SON with, say, mod 2 coefficients, or SON with a ring where 2 is invertible. So, yeah, I did this at some point. Mod 2 coefficients, you get Stiefel-Whitney classes. If a ring where 2 is invertible, so not a 2 torsion group, then what you get is, if it's odd, you get polynomial in the Pontryagin classes. I should have a B, my mistake. In things called the Pontryagin classes. I should move this so that I can actually write this down instead of squeezing it in. So this is when n is odd. And otherwise, you get P1 up to Pn and an Euler class, n over 2. And the thing is that E squares to Pn over 2. So these are values that you can compute by inductively using the Gysin sequence. And BUN has Chern classes by using the fact that compute with these fibrations. So if you start with, yeah, so the BSON one is easy to just state. So if you take the universal n-plane bundle over BSON and you take its sphere bundle, it turns out that you get BSON minus 1. And there's a similar thing that happens for BUN. Where you get, how big are things? This should be like S2n minus 1. Yeah, so the existence of these as fibrations comes from the following fact. So if G is a topological group, H is a topologically closed subgroup. So when I say closed subgroup, I mean like it's closed as a subspace. Then we have a fibration sequence. There's the one that you would expect. So if you take the quotient of G by H, right, this is going to be a fiber bundle unless something really perverse is going on. But you actually get to continue looping, or sorry, de-looping. This is kind of the inverse of the Pupa sequence. You can actually de-loop to the right as long as your things are still groups. And you get to de-loop one more if G mod H is actually a group.
What if it's a stack?
What if it's a stack? Oh, that's a good question. I haven't thought about this in the language of stacks, so maybe later.
Yeah.
So the point is that this is a fibration sequence. And in particular, maybe I hope this isn't too low, but if you think about this, so BH, what you can do is start with the construction of BG. So, oh, I did this wrong. My gosh. I'm like totally off the walls today. H is the smaller thing. H maps to G. Okay. All right. So if you take BH, start with the construction for BG. Choose some space EG that has a free action by G so that the quotient is actually a fiber bundle. So call that EG. So since EG is contractible, you can also have H acting on it in a free way and consider its quotient. And as long as everything's fine, this is going to give you a model for BH. But we can re-express this in terms of that, I should write a homotopy equivalence here. In terms of this action product that I love so much, you take the principal G bundle EG times over G, replace the fibers with BG, or sorry, with G over H. So you can tell that this works because the G's cancel out. So in fact, you construct BH as the universal bundle EG with the fibers replaced by G mod H in this way. But that's exactly what's happening up here. You start with, well, this is the sphere bundle, the associated sphere bundle, right? If you start with, fine, I'll just keep going. Okay, we're going to get to transgression sometime. Trust me. I don't have to go off on this tangent, but I am. Okay. Right, so if you start now with E, SON, so for example, you could take like frames in R infinity, and you take, and you plug in over SON with the sphere of degree n minus 1. So you choose the representation on the n sphere so that when you plug it in, you get the sphere bundle. But this Sn minus 1, we know this to be a homogeneous space of SON mod SON minus 1, right? And so indeed we do get our SON mod SON minus 1, and this is going to be a model for BSO n minus 1. So this is like a heuristic way of seeing why the sphere bundle of the universal bundle, which you can make by just taking the universal principal bundle and plugging in the n's minus 1 sphere with the usual action. You just have to reason, the only way that you have to do to make this rigorous is you have to reason that the action of this space on the sphere, when you make the identification of the sphere with this quotient space, then this action is the same, which is actually not too hard to see because this is sort of, by definition, what that quotient means. So yeah, that was a wild tangent. This was just the context for the Gysin sequence, and now I should actually show you how to find it in the Serre Spectral sequence.
We defined the product in the character in the Tom space or the Pontryagin Tom.
Something, yeah, maybe, I forget.
I don't know if we defined that last time.
Yeah, I've defined it a few times. I should define it again. So if X is a right G space, and if Y is a left G space, then we define X cross G with Y to be, how does this work? You take X cross Y and you mod out by something that looks like XG comma Y becomes X comma, my commas look like G's. Yeah. So the relation you introduce allows you to switch a comma and G. That's what it does. And so you get two projection maps. They don't map to X and Y, but they map to X mod G, and they map to Y mod G. So you do get two natural projection maps, but you have to, they're only well-defined modulo the action of G. And so if G acting on X is free, I've drawn it on the wrong side, please bear with me, then basically X mod G Y is like replace the G orbits in X with copies of Y. And then you can go and I give it as an exercise. If it isn't a free action, what you do is every orbit gets replaced to Y modulo the stabilizer subgroup associated to that orbit. So this is like you're starting to get into like stack territory. Yeah, okay, very cool, good question. Okay, so now where does this Gysin sequence find itself within the Serre spectral sequence? And I'm probably not going to have time to get to transgression because I've just been blabbing. I'm not sure if people want to hear about cohomology operations today. It's a kind of a completely orthogonal, but not really orthogonal topic. Okay. Where is my, did I even figure this out? Come on, okay. So let's look at Gysin in Serre spectral sequence. Okay, so let's suppose we have our sphere bundle E B. Okay, and so let's say our sphere lives in degree n minus 1. So here's our mu, our favorite mu class, and the cohomology of the fiber is saying that there's nothing else in that entire column. So this is our Q. Yeah, let's not get ahead of ourselves here. Let's write this down. Okay, 0, 0. So okay, so let's consider. I'll only identify one of the maps, I guess. Okay, so let's consider something in degree k. Let's consider something in degree k of E. Okay, and so in terms of our spectral sequence, we have two rows that are potentially non-zero. So this entire thing is 0, and this entire thing is also 0. So if we're trying to figure out degree k cohomology of E, this is only going to intersect our non-zero stuff in two places. All right, so here and here. And this whole row is isomorphic to this row. So let's say it like this. E2 of P0 is isomorphic to E2 of P comma n minus 1, where the isomorphism going to here is given by sending alpha to, say, mu times alpha. So whatever you have in this row, you can bring it up to this row by multiplying by mu, and that's an isomorphism. So in particular, what you can do is consider the part that ends up here. Okay, what degree is this? We know that it has to add up to k, so whatever it is plus n minus 1 has to be k. So this is k minus n plus 1. And so if you want something in hk of e, that means it has to be in the kernel of this differential coming out on d, what page is that, dn? So you're going to need to find something in the kernel of dn in degree, what am I trying to say, man? Okay, look. So this is in degree k of e. It's in one of the filtration quotients. It's in the topmost filtration quotients. It's well-defined modulo whatever this is. Okay, and you can map it directly down to this, which is hk minus n plus 1 of b, by just choosing this to isomorphism, right? So mu times something just goes to the thing that you multiplied mu by. So from the E2 page, right, so this is all happening on what? The E, say, yeah, let me think about it. How does this work now? Okay. Yeah. I think this is it. All right, I'm having the brain fart moment again. So what's happening here is we have something in degree k of e. We know that we can find it somewhere on this filtration line. We're only looking, according to this sequence though, why do I have e? Because this is abstractly homeomorphic to the cohomology of the sphere bundle. Oops. Yeah, E is the sphere bundle. Okay, E is the sphere bundle. Over here, it's written as SV. So we have something in HK of SV, and we want to figure out what is the item that we want right here. So in order for this sequence to be exact, though, we want to pick something in like HK of, what am I trying to say? No, I had this figured out like one day last week and I've forgotten already. But this is the map. This is your del bar. Essentially is going from this part of the cohomology of E down to this part in the cohomology of B. And it's only well defined up to whatever this is. And I forget how to get rid of that ambiguity. Yeah, I said in my abstract that finding the Gysin sequence inside Serre Spectral sequence is instructive, and I guess I just didn't instruct myself well enough. Yeah, but this is the way. So the other maps are kind of, it's clear where they're supposed to come from. This is kind of not super clear how you're supposed to find this del bar, but this is sort of the only way that you possibly could do it. And then we want to say, okay, maybe you want to argue that the del bar, image of del bar, is in the kernel of cupping with E. This is something that happens kind of at the universal level. So if we took BSON and BSON minus 1, you would have an Euler class living in degree n. So here's an Euler class for whatever our sphere bundle is. I'll just call it E. And this is living in degree n. And universally what happens is that this, the Euler class, when you have it in BSON and you pull it back to BSON minus 1, it goes to 0. So in the universal spectral sequence, that's saying on the E2 page, you have this E sitting here on the E2 page. By the time you get to the E infinity page, it's gone. So it has to get hit by something. And the only option is one of the generators of this group. So universally, this mu in the fiber hits the universal Euler class. So in every sphere bundle, at least the ones that come from vector bundles, the generator of your sphere cohomology is going to hit your Euler class. So what am I trying to do to relate this to exactness? What am I trying to say? I'm trying to say that, in fact, this, in general, dn of x I guess this is something that I have no, I'll write it here. So essentially what's happening is that if you take your x in this class and you push it down del bar of x, and then you cup it with the Euler class, that's actually the same as the differential. So dn of x is actually equal to del bar of x cup with the Euler class. And so if your x is actually representing an element in the cohomology of E, it needs to be a kernel. It needs to be in the kernel of Dn. It has to be a permanent cycle. And so if x is in the kernel of Dn, that means that del bar x is in the kernel of cupping with E, right? And so this means that del bar is in the kernel of cupping with E. This is kind of a really funky argument to find inside of the spectral sequence. I didn't do a really good job of it. But this is how you can at least show that this composition is zero. This doesn't, I haven't shown that this is like exact, but this is one of the steps in showing that like this really weird function you find inside of the spectral sequence as actually giving you this strange co-boundary map in the Gysin sequence as we wrote it down over there. So I should probably like step away from this example now. It's starting to get really cluttered, and let people figure it out on their own, because that's the best way to learn spectral sequences. Because everyone's just watching me up here like, how does this work? And like, it's a lot more instructive if you figure it out. I'm kind of just teaching myself by giving seminars to you. It's completely like self-indulgent, and I hope it's helpful to the audience. Okay, how much time do I have left? I might be able to do transgression.
You have 30 minutes.
All right, let's go. Let's do completely different stuff. All right. I should also mention there's an analogous spectral sequence called the Wang sequence. I would probably get yelled at for not mentioning this. This is for fibrations where the base space is a sphere. So there's a similar sequence. I didn't figure it out in the way that like I figured out the Gysin sequence, and so I'm not even going to write it down because I wouldn't be able to explain anything. But you can go and play around with the spectral sequence and try to derive that. Go look it up on Wikipedia and see what it's supposed to be. Go figure that out, yeah. What's interesting about the Gysin sequence is that you find this Euler class just hanging around menacingly. It's just always there. No matter where you go, here it is. Okay. How do I explain transgression? Okay. So remember in the Serre Exact Sequence where we use the differential as a morphism, like in our exact sequence, because in that certain range that we had, we were still able to identify the column values with the cohomology of the fiber and the base values with the cohomology of the base space. And so the differential on like this En plus M page could still be interpreted as a map between those two groups. So transgression is like a more subtle version of that, where it's not defined on all of H, and the value is actually just a coset in the cohomology of B. So let's draw pictures, and let's talk about what we mean. Okay, so here's this. So N. So here we have the En plus 1 page, and the En differential, N plus 1 differential takes us down to the bottom row. N. Okay. All right, so tau is a partially defined and coset valued function, quote unquote. Do you have to low, or are you just backing
I
up?
have to go in a second.
Okay, sure. Let's see here. Okay, so the point was that, remember, the E2 page was our Hn of f. And to get down to this, there's a whole bunch of evaporation that happens, so this is a subset. Over here we had hn plus 1 of b, and to get down to this page, we had a quotient. And so the idea is that if x is in en plus 1, 0, n, or let's say if x is in hnf, let's say this differently. If x is in z n, this is an n plus 1, contained in hnf, where we remember this means that the first n differentials vanish. Differentials vanish. So if the first n differentials vanish on your x, then the dn plus 1 is actually defined on it. It lives inside of the subgroup of f where dn plus 1 is defined, and you can actually get this arrow. And dn plus 1x is going to land down here is a coset of the image of dn in hn plus 1b. So what we do is we kind of write in with a dotted line tau going from f to hn plus 1b, knowing full well that it's not actually defined on all of f, and that the value isn't actually necessarily a single value in b, but rather an entire set worth of values. It's not well defined. So in the Serre exact sequence case, we were in the best possible scenario where this group was equal to this, and this group was equal to this. And now we have to sort of play around with this ambiguity. So here's some language. So x, yeah. So this is what means x is transgressive if it lives in this subgroup. Okay, and we say that y is in the transgression of f, or y, do I say, yeah, y equals the transgression of f. It's not a great notation. If dn plus 1 of x, so if first of all x is transgressive, and if the differential applied to x is in the coset given by y. Right, so they have the same, right? Okay, except I called this bn, right? I called this bn. Okay. NH. All right, see you. All right. Okay, so this is what we mean to say that x is transgressive. This is what we mean to say that y is the transgression of x. And we're going to say, notice, so tau is defined on all of h and f, if and only if what? Yeah, dr coming in to this spot out. So, yeah. So this subset equals f if and only if every outcoming differential is 0. On the other hand, tau is single valued if all of the incoming differentials on the bottom row, where we want to compute our B cohomology, are 0. So, oh yeah, all of these incoming ones are 0. So exactly in the case of our Serre exact sequence, all of the outcoming things coming out of our boundary were this, all of the incoming things into our bottom row were 0 in that particular range. So, yeah. So here's a black box to determine whether an element is transgressive or not, coming from just a criteria coming from the spaces themselves. So this is a criteria that's like external to the spectral sequence, and it gives us information about the spectral sequence. So I need to start citing stuff because I'm just pulling this out of books at this point. Mosher Tangora, their cohomology classes book, sorry, cohomology operations book is really good. And then I also had, I just ran into Fomenko and Fuchs like yesterday. Never actually looked in this book before, but it's really good. So here's a principle. So consider the pair of maps. So we have P as a map from E, total space, relative to the fiber, mapping to the base space relative to the base point, right? The fiber over the base point goes to the base point. And the co-boundary map in the long exact sequence of the pair for E and F. So then, it turns out, so X is transgressive if and only if the co-boundary of X is in the image of P star. So what the heck? Okay, let's draw these groups. HKF mapping to HK plus 1. Sorry, this should be relative. And then we have a P star. So this is del, this is P star coming from the reduced cohomology of B. And it's in fact, and these y's are said to be the values of the transgression for F. Okay? So this is a cute criteria. I should have written it over there because I'm about to apply it. Oh my God. Is it worth it to do this? We'll find out. Here we go. Is any of this really worth it? Okay, useful lemma. So this is kind of the lemma that introduces cohomology operations as a useful tool in spectral sequences. So suppose we have a sequence, say eta n, going from hn cohomology and g coefficients to h, let's say n plus k cohomology with h coefficients for each n. We have one of these natural transformations of sets. Yeah. So you could consider natural transformation of groups, but we actually only want to consider sets. There's cohomology operations such as the squaring function, which are not homomorphisms. So you actually want to consider natural transformations as sets to capture all of the cohomology operations as sets. So set-valued functors. Suppose this is one of those things, so that for all pairs XA, we have the following diagram commuting. So of XA. So you consider the long exact sequences for the pairs with these two different coefficients. And then you apply your natural transformation vertically to both of these things. And you're supposed to see eta n of A, eta n of x comma A. So this has to commute. And this is a double arrow. Yeah. So you want to consider all of these families of natural transformations so that these squares commute. These are exactly the squares that we wrote over there that weren't induced by a function of spaces. And so then, if x is transgressive, so is what? Eta, let's say if this is an n, eta n of x, and this is with g coefficients, eta n of x in n plus k f h, and the transgression of this modified x is just you apply the operation on the transgression of x. So this looks like a really weird, demented thing that, why would this ever help? Well, the point is that if you can do enough calculations to get a good grasp on what is like the algebra of all cohomology operations for a given coefficient system, or at least all of the ones that satisfy this strange condition, then you can do a lot of powerful things. Once you identify one element that's transgressive, now you can just start hitting it with cohomology operations to produce more and more transgressive elements. That means that once you look at all of these, like tau of x for your transgressive elements, sorry, no, your etas of x, that you like push up to make a new element, when you're looking at the differentials coming out of that, you already know that they all have to be 0 until the very end. And that, right, by knowing in advance that something's transgressive, you know all of the differentials except for the last one are 0. You get this sort of like insulation of transgressive elements, where you already know a whole bunch of stuff about differentials coming out of them. So this condition here, I'm going to say, so this condition here, star or whatever, this is related to stability. So stability says something much, much similar to this, except it doesn't say anything about pairs. Instead, you have your suspension isomorphisms. Same coefficients, yeah. Or different coefficients. Yeah, same coefficients, yeah. So you take your suspension isomorphisms, and you want to apply your cohomology operation. So stability means that these squares commute. So this is eta for x. I guess it's got a single value now, eta n of x for the space x, and this is eta n for the space suspension x. So this square says stability, this is what we want. It turns out stability implies this. Implies this. And so what we can do is we can only think about stable cohomology classes, cohomology operations. And so, well, okay, what does that mean though? So what is a cohomology operation going from here to here? Well, by the Yoneda lemma, right, you're actually looking at maps from the Eilenberg-Mac Lane space Kan to the Eilenberg-Mac Lane space Kb n plus k. And this is going to be the n plus kth cohomology of k, a, n with b coefficients. So in fact, right, our cohomology operations that we're thinking about, they already live in groups that we've already kind of studied before. And so if we take like a stable limit, it turns out that the stable cohomology operations are precisely describing the ones that survive in this limit, or like exist in this limit. You know, this is a really bad explanation of all of this, because this isn't a talk on cohomology operations. It's a talk on the spectral sequence. But these are really related subjects, and so, you know, feel a little bad not doing a better job given the entire context. But here we are. So we're interested in the stable cohomology operations, and these in mod 2, let's give some examples in mod 2. Oh, here's a great example that you can do by hand, which I should at least mention. Actually, how much time is there now? 15? 10 minutes. Okay. I'll skip Bachstein's. They're really cute. You can do them in like any coefficients. So I should mention Steenrod squares. And then write down at least the E2 page of the example I wanted to do. Okay, so in mod 2 coefficients, there are really special classes called Steenrod squares. So mod 2 coefficients. By which I mean over here when we're talking about these natural transformations, I want G and H to both be Z mod 2. For all I bigger than or equal to 0, there are these classes called SQI. And they take your cohomology with mod 2 coefficients, and they increase the degree by I. So I put a star here to denote that it's actually a sequence of classes. There's one for every star. But in sort of the stable limit, there's just one class living in the Steenrod algebra. And this is a stable cohomology operation such that two properties happen. If you apply it to some element in a homogeneous degree, you get 0 if that degree is less than I. You get alpha squared if that degree is equal to I. And you get just the Steenrod SQI is 0 if, it's the identity of I is 0. So SQ0 is the identity, is what that last one means. If you have SQI, where I is the degree of your alpha, you're actually squaring alpha. So like I said earlier, squaring is a natural transformation. It is a cohomology operation that isn't a group homomorphism usually, but in mod 2 it is, because of the binomial theorem. So in general, raising to the pth power is not a homomorphism, but modulo p it is, by the binomial theorem. So these are actually give you homomorphisms, in fact. And then we have some interesting thing called the Cartan formula. If you apply square to a product, what you get is something that looks almost reminiscent of the Whitney sum formula. Sum over all p plus q equals I. You square p of alpha times square q of beta, where times means cup product in whatever cohomology ring you're working on. So these generate an algebra, and it turns out these generate the algebra of all stable cohomology operations for Z mod 2. So A2 Steenrod algebra and this is equal to generated by the set of all Steenrod squares, I greater than or equal to 0, modulo these things called the Adem relations. I'm just going to write them down. The idea is you use these Adem relations to kind of simplify your expressions in order to make them more like normal form. So there's an entire story here about Steenrod algebra that I should really talk about, but I don't actually know it yet. So this is the Steenrod algebra of mod 2 cohomology operations. They're generated by Steenrod squares, and we do have relations between them. It's not just some free polynomial thing. It turns out that as a multiplicative thing, multiplicative generators, you can use the Steenrod squares where I is a power of 2. That's a minimal set of generators for the multiplicative structure. And of course, Serre proved that. That was a proof of Serre. Okay, so I'm not going to get very far into this because I think I have 3 minutes left. So let's just start. Let's do the cohomology of KZ3 with mod 2 coefficients using this fibration, path loop fibration for KZ3. There's nobody here. Just talking about spectral sequences. There's nobody here. Okay, so the tower, we know the column. So I'm actually just going to skip. I'm going to skip odd things in the column, and it's not going to cause any problems. Okay, so there's a bunch of rows of zeros, but in between them we have the polynomial ring generated by iota, which gives us the cohomology for KZ2, which is also called CP infinity. Yeah. let's not forget. And I need to write down HP KZ3 HQ CP infinity. Always write that down. Okay, so here's that. So KZ3, we know that 0, 1, 2 are all 0. First non-trivial homotopy group is a Z. That carries all the way up to cohomology. You get H3 is a Z. We know that we have to clear everything out. So of course we get iota hits Z. So we also know this whole column. So let's call this mu. So we have iota mu, iota squared mu, iota cubed mu, iota 4 mu, iota 5 mu. So we know iota hits mu, okay? But then what we can do, so here's right off the bat, iota is transgressive. But what this also means is that iota squared, which is SQ2 iota, is transgressive. We also know that iota to the 4, which is SQ to the 4 SQ squared iota, is da 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 da. So in general, knowing that iota is transgressive, you can do like this: SQ2 to the k, SQ2 to the k minus 1, da 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 da, SQ2, and then you won't have SQ1 because there's a odd rows that I've neglected to put in, which is maybe confusing now that I think about it. So these guys all transgress. So iota, iota 2, iota 4, iota 8, all transgress. So that means that they're like insulated from our spectral sequence. If you went through and you actually did the calculation, you know, the Leibniz rule modulo 2, Leibniz rule is going to say that all of the outgoing differentials, whenever the power of iota is even, those are all 0. And whenever they're not even, then they all map onto this. So yeah, so mu gets hit by iota. This being 0 means that this stays. This being 0 means that this stays. Once we got rid of iota, it turns out that every odd multiple or odd power of iota gets cleared out. All of the even powers stay behind on the next page. So this is what, the E3 page. So let me just like draw this, and then I'll maybe leave the rest as an exercise, because it's fun. Of course, I made a mistake. This is Emod 2. Somebody should have caught that. So on the next page, we hit mu. Mu's gone. Mu's not there anymore. Iota doesn't go to 0, so it's not there anymore. Iota squared is there because it did go to 0. Iota to the 4 is there because it did go to 0. So now, right, you just continue to play the same game. You know iota squared transgresses, so there has to be something here that it transgresses to. That thing that it transgresses to has to be, well, actually, no, it's not here. It's in degree 5. There's nothing that can hit the thing in degree 4, so there can't be anything there. But in degree 5, your iota squared has to hit something. It has to be SQ2 of mu. And you can call that a new element, say beta. And so it turns out that all of these and give polynomial generators for H star K, Z, 3. Yeah, if I had more time, I'd spell this out, but I think we're like way over actually now. So this cohomology ring, Z mod 2 coefficients, is actually a polynomial ring over Z mod 2, whose generators are all of these Steenrod squares. Sequences of Steenrod squares that are increasing in powers of 2. Basically, you're just successively squaring iota and then taking its transgression. So dot, 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 I'll dot, dot, dot this one. Dot, 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 square 2 of mu. Because mu is the transgression of alpha. So all of these things transgress to this stuff. And it turns out you have to go and do the calculation to show that there are no relations between these. This is what you get for this cohomology ring. Okay, so yeah. Sorry for going way over time.
No, worries.
But like, yeah.
You have 9 seconds.
I have 9 seconds left. This is a special case of something called Cartan's theorem. So Cartan's theorem, I haven't presented the language to even state Cartan's theorem. This is a very special case of Cartan's theorem where this fiber has a simple basis given by iota. And you're just looking at all of the admissible transgressions of iota with excess 0. So this is Cartan's theorem, and Cartan's theorem, of course, guess who? Serre computed. He used Cartan's theorem to compute the cohomology of K. I think he did KZN for any Z mod P coefficient. So mod P coefficients, you can just do it. You can do it using transgression techniques, and you can try to do it by hand, and you get kind of overwhelmed. And you end up running into, okay, we actually really need Cartan's theorem. You might even stumble into it as you try to do more difficult computations. Cartan's theorem gives us a bunch of Serre calculations for the mod P so that the difficult cohomology for these KZNs is the integer cohomology. That's much more difficult to compute because it has contributions of P torsion from all P. So when you go to Z mod P coefficients, you're ignoring Z mod Q stuff for Q not equal to P. But when you do Z coefficients, you get all P. So like my challenge for you that I'll leave as the last thing, I'm way over 9 seconds now, is just try computing the cohomology of KZ3 with integer coefficients. So you can do it for a while, and you'll probably get stuck at some point. Try to do it until you get to Z mod 5. So do this until you get a Z mod 5. At least that's the challenge. Okay, thank you for putting up with the long talk. Thank you. Thanks, everybody.
All right. Do you have any questions? I guess not.
Do you have any questions?
I don't.
You're too sleepy for questions, I think.
Yeah, I might have questions later.
Sure.
I'll ask on Discord.
Okay. Thank you. Thank you, everybody. Yeah.